Hello world, and welcome back. Today we're going to be talking more about circles, specifically about tangent lines to circles. Some of you may be familiar with the word tangent in terms of a trig function. There may be a connection, and I probably should know that, but for now, let's just focus on the fact that a tangent line drawn to a circle or a curve, for that matter, is a line that intersects that curve or circle in exactly one point. So it just barely nicks off of that thing. So if you see this little note-taking guide that we have here, it says a tangent intersects a circle at exactly how many points? 1 point. Called the point of tangency. The boldface terms there are just the vocabulary you need to know. Okay, now here's a fun little theorem about tangent lines drawn to circles. A line is tangent to a circle if and only if it is blank to a blank drawn to the point of tangency. It's going to be to a drawn to the point of tangency. So that's a really fun and interesting property. Once again, perpendicular means forms a right angle, and if you get a right angle, then now we might have a right triangle. And if we have a right triangle, Pythagorean theorem is in play, so be on the lookout for that. So we know what a tangent is. It's a line that intersects a circle at exactly 1 point. And we know a property of the tangent, and that's going to be that a tangent line, when it's drawn to a circle, if you connect a radius or a diameter to the point of tangency, tangent line and radius, diameter, forms right angle. So let's just look at an example of trying to determine if something is a tangent line drawn to a circle. So in this particular instance, they're not using a line, they're using a segment, and they say, hey, determine if AB, segment AB is tangent to circle P at point A. A is a question. So if it was in fact tangent, it would form a right angle at A, right? That we just learned that. So how do we determine if A is a right angle? Some people might be thinking, like, oh, let's use inverse trigonometry. I remember that one. Well, we don't really have inverse trig for right angles. I mean, yes, you kind of can do that, but we didn't really learn that. How about the converse of the Pythagorean theorem? That's when we say, well, if the sum of the squares of the shorter sides is equal to the square of the longest side, then we have a right triangle, and then that would mean that if that's a right angle there, then we have a point of tangency. Okay, which means the line is tangent. So let's go 17 squared blank 8 squared plus 15 squared. So 17 squared is 289. And 8 squared plus 15 squared, just did this before, is also 289. They're equal. Therefore, AB is tangent to circle P. All right. So let's say you do a problem like that. In this particular instance, they say if JK is tangent to circle L, I mean, they're assuming if, that means it's true, then find X. Okay, so we know that that we have a point of tangency at J, in this case, of number 3. So they want us to find X, and so now we're not using the converse, we're just using regular Pythagorean theorem. So it's going to go X squared equals 7 squared plus 19 squared. X equals the square root of 7 squared plus 19 squared. X would be about equal to 7 squared 19 squared, and then take the square root of that. 20.2. So that's pretty much what they're looking for in these scenarios. And you see in both situations. One, we're trying to determine if we have a right angle so that we can show that we have a tangent line. And then when you're given that you have a tangent line, you know a right angle is formed, you have your radius length, and you have all of these other lengths, but you're missing one, you have to use the Pythagorean theorem. Let's look for one that might be a little bit trickier. Here, number 8. So why don't you pause the video and try to do number 8. Okay, welcome back. So you may have determined here, so we know that KJ is tangent, so we're going to have a right angle. And X is just the length of JL. We need to know what JM is. So we know that LM is also X because it's a radius. So this is 2X. And now we can go ahead and use the Pythagorean theorem. So we have 2X quantity squared plus 7 squared equals 25 squared. 4x squared plus 49 equals 25 squared. And I should know that, but I'm just not going to mess around. That's what I thought. 625. Then we're going to subtract 49 from both sides. So we have 4x squared equals 625 minus 49. Divide both sides by 4. Minus 49 divided by 4. And then ultimately we're taking the square root of that. So I'm going to go 625 minus 49 divided by 4. 625 minus 49. Let's make sure that computes. Yeah. All right. All divided by 4. That's 144. Oh, awesome. So the square root of 144 is 12. So that works out to be, here, let's go like this. When I divide both sides by 4, we get x squared equals 144. Take the square root of both sides. X equals 12. All right. Moving on. So there's a couple more things to ponder when we're talking about tangent lines. So if you have a point that's outside of a circle and then you draw a tangent line to the top and the bottom of the circle, I mean, that's how it's oriented. It could be the left and the right or whatever. It's just basically you connect two different tangent lines to the circle as you see in this particular instance. You have an external point B, and you're going to connect B to A here, and you're going to connect B to C there. Now, A and C are both points of tangency, right? You can see that with the right angles that are formed. So it would follow, this is a theorem, that the distance from A to B would have to be the same as the distance from C to B. That's just a fun fact. Okay, and that's provable. I encourage you to do so, but we don't really have time for that right now. And the other one is, so if a circle is, if a polygon is circumscribed around a circle, then all the sides are tangent. So technically the definition of being circumscribed around that circle is that in order for it to fit that description, the shape has to touch the circle at exactly one point. Okay, so you have the points of tangency D, E, and F. And that would be it. Again, another way to say that is if a circle is inscribed inside of a polygon, in order for it to technically be inscribed, every single side of that circle would have to be tangent to the, or sorry, every single side of the circle, every single side of the shape must be tangent to the circle. So, and that's it. So that's basically like just defining what it means to be circumscribed around or inscribed inside for a circle. Okay. So now the rest of the exercises pretty much are just applying that vocabulary. So the directions say find each value or measure. assume that the segments that appear to be tangent are tangent. So it's important that they say that. If they didn't say it, then we don't know this. So let's just try something like number 10. Why don't you do number 10, and I'll pause the video or you pause the video. I mean, I'm gonna keep working, but all right. So you see that they're tangent, and we just learned that if we have an exterior point and it's and through that point you have two tangent lines drawn to the circle, the distance from the exterior point to the points of tangency are going to be congruent. Therefore, we can now set 8x minus 19. That's a weird 8. Deal with it. 5x plus 23 minus 5x plus 19 plus 19. And that is a 23 that I attempted to draw there. And that didn't quite work out. So 5x plus 23, 8x, 19. Okay, so we have 3x equals, because that's gone and that's gone, and that's going to be 32, right? Yes, 32. Oh, wait, no, not 32. I do this all the time. That's 19. So if we had added 20 to it, it would have been 43, so it's going to be 42. Okay. And yeah, divided by 3, x equals 14, I believe. Yeah. So there you go. Okay, so let's take a look at like number 12. Number 12, they want us to find SV, so this is kind of slightly more multi-step. I think they, let's just highlight the part that we need to find. We need to find this green segment right here. Things we know ST and SU are tangent to the circle. So ST and SU are both equidistant to the circle, or S is equidistant to the circle on both sides. So we can therefore mark these as being congruent, and then we go ahead and solve for x first. So 10x minus 41 equals 4x plus 7. Means we have 6x equals 48. X equals, that's going to be 8. And sorry, don't know my times tables. So I found x, that's wonderful. So we're going to plug that in. We have if we plug it in for 4, it's going to be 32 plus 7, which is going to be 39. Or if you plug it in over here, it's going to be 80 minus 41, which is also 39. Awesome. So now we have two triangles that we could potentially solve for. I'm going to call this side, we'll call it Z. Actually, you know what? Let's call it T, little t, right across from the big T there. So let's solve for side T. So that means we use the Pythagorean theorem. So shrink this guy down. And we have T squared equals 17 squared plus 39 squared. So T is going to equal the square root of 17 squared plus 39 squared. Notice how I do that. I don't have a calculator handy, so I just do it that way. 17 squared plus 39 squared. Gotta work on my 9s. Let's do them normal. Okay, so 17 squared plus 39 squared is 1810. Take the square root of that, and you get 42.5. T is about 42.5, meaning the answer SV equals 42.5. All right, and all right, let's do one of these. Let's just do number 13 and call it good. So they want us to find the perimeter of triangle DEF. So why don't you pause the video and see if you can do this on your own. Just keep in mind that D, F, and E are all connected to tangent lines. All right, welcome back. So what we're going to do is we know that DG and DH are both the same because they are the tangents drawn from an exterior point. HE and, ooh, that was cool. I didn't mean for that to happen. HE and IE also the same. They're both 16. And FG and FI. Now that we have all these wonderful congruent marks, I can now label other measurements And then the rest is just going to be perimeter equals 2 times 16 plus 2 times 9.5 plus 2 times 11. So it's 32 plus, what's that, 19 plus 22. 32 plus 19 plus 22. 2, 19, 22 plus. Let's try that again. Ooh. Okay, 13 plus 19 plus 22 equals 73. Okay, so P equals 73. All right, that's it. So, hopefully that was helpful to you, and good luck with your tangent lines. Oh, P.S. That cat that's back there, if you've been paying attention to the cats in the background, you can also just enjoy the entire background. That right there, it's Master Gifu. That's not Bowie.